Am I audible in the back? Perfect. So, what were we doing in the last class? Well, proximity effect, physical design. What were we doing in the last class? We reviewed the row decoder, we reviewed the address decoding, and then we looked into the physical design of the row decoder and the well proximity effects. Any questions from that? How we were doing the via programmation. Okay, so what have you understood of that?
Basically, when we are considering the annual proximity, then all the transistors which are closer to the anvil, they should be at equal distance. So in that part, we are applying that here. It is known, but how we are actually doing that?
Oh, you're looking at the mechanics of how to do via programmation. So you remember this lecture on automation that we had with Ashu Talwar in the last semester? So in that lecture, he told that in scripting or whatever layer you have in your layout, you can always identify through the layer map table which layer you are interested in. And you can put labels in a particular layer that you can define in your layout. You may call it a programmation layer. Okay. And over there, you can put labels like drop VR, drop VR, drop VR, drop VR. And then through a simple software loop, you can see, okay, you can scan any particular cell, say, okay, where is the drop VR label there? And where there is a drop VR label, if you want to drop a VR1, you can actually make a VR1 based rectangle or a square so that that label is replaced by a real VR1. So programmation, so this is the bilkul ground level mechanics of it, that you put some labels at different places and those labels are identified by your software tool, and that software tool will replace that label with the desired, whether it is a VR or a contact or a metal stub, whatever it is, it will replace it with that particular shape, and your layout will appear different after that script is run. Is that what you are asking? Exactly. In ROM also, the programmation is done exactly like this, that you tell where, which. So now here you have to have a logic in the sense that where will you put all those VR1 labels? You will put drop VR, drop VR, drop VR, drop VR labels beneath all the metal 2 lines that you're using for programming your metal 2 lines, which are outputs of your, let us say, 2 to 4 decoder in the pre-decode region. So beneath that, wherever you have the intersection, you will put those labels. Now, which label is to be used for dropping the VR is a part of your logic. Okay, in the first row, replace the label with a VR1 at the first drop VR instance. Second row, replace at the second drop VR instance. Third row, do it at the third drop VR instance. Fourth row, do it at the fourth drop VR instance. Fifth row, again come to first, then second, third, and fourth. So this is how you will be able to build the program, what do you say, structure that was shown in the slides that day. This kind of a structure there, where the red dots are the places where you have dropped the VR, but the label was put at all the intersections. Are you able to see this? Any questions? So you have to put labels in your layout, and the script has to replace those with the VRs. Okay. Any other questions about well proximity effects or layouts of row decoders? There were a few questions in yesterday's office hours. I believe they are resolved now. Anything else? So why do we use multiple row decoders, or why do we so see, in terms of schematic there is just one row decoder that we have. Hmm? But when it came to layout, we said we will make a layout out of four row decoders. So one row decoder will select four rows instead of one. Why do you do that?
To decrease the input NAND gates, like so to increase the repeatability of the structure. Say we can just put the same structure below and then we only need to do VR programmation. We don't need to make the same structure again and again.
Okay, and anyone else? Many of you may not have heard what Madhav said, so even if you repeat the same answer, it's fine with me. Why do we want to club multiple row decoders or multiple word line selection generation circuit into one row decoder? अभी पहले इसका जवाब हम्म
You are basically asking like we are having the multiple rows and instead of that we are selecting one long column and
no, I'm not asking anything like that. I am saying in the videos we had clearly said that you will not make a row decoder per word line. You will make a row decoder for a pair or a four set of word lines or eight set of word lines. Why do you do that? To reduce gate count, because we can do much more sharing. See, unlike standard cells where sharing was prohibited, we always kept half DRC. In memories, in the memory cell itself, we saw that we want to do much more sharing. We were sharing VRs across four cells, contacts across two cells, so many things we were sharing at the boundary of the memory cell. And what I want to emphasize to you is that the similar philosophy continues in other cells also. Like in row decoders, we understand that, okay, the LSB will choose the final word line. For LSB, I need to have a full decoding logic there. But for the MSBs, they will be exactly the same for adjacent four rows or adjacent eight rows or whatever. So I can have that part of my decoding done only once. Are you able to see this? So it's kind of adding a level of hierarchy into your decoding, which already is there. We are looking at them as stages as of now. But as soon as you cluster them, as soon as you club them, you add a level of hierarchy. And that reduces the gate count, that helps you reduce leakage, that helps you have lower capacitance on the programming lines, and therefore it is advantageous. Now, is it necessary to do that? No. But would you want to do that? Yes, because there is a clear set of PPA advantages that can come out of this. Okay? Yes, you had another question.
so could you explain this one again? I didn't know.
So, when we say that there is multiple stages of decoding, what are we saying? That okay, uh, we will do pre-decoding, 2 to 4 to 4 to 8, and so on. And after that, it could happen that my post decoder still has to have a 5 input NAND gate. So what do? You say, okay, for 5 input, I will add the last 2 bits in the last stage. And the remaining 3 bits, I will and or whatever in the previous stage. So you're doing it in stages so that your stack length is contained, it is limited, so that you get the right speed. Now, if you have used 3 MSBs in the first stage, then the output of those MSBs is going to be the same for, let us say, so 5, 6, 7, and so we had a 3 to 8 decoder for address bits 5, 6, 7. And you were selecting, because this was, let us say, row 0, row 1, row 2, let us say. So This zeroth output of this decoder was going to all of them. Are you with me? So the zeroth was going to all of them because you had to select row 0, row 1, row 2. And of these three, 0 was going here, 1 was going there, 2 was going there, and so on. You do realize this NAND gate had exactly the same set of inputs for all these four rows? Are you able to see this? So what you say is that, okay, instead of using four NAND gates, which have exactly the same inputs and exactly the same output, I will instead use one NAND gate. Again, let the 0 come there, and it will go as an input to all the four of them. I have reduced 3 extra NAND gates in this setting.
So this setting, you are actually using only the bits 4 and 3.
No, I'm using 5, 6, 7 also. For 5, I'm also using 5, 6, 7 because for row 4 or row 16, let us say, one of these bits, instead of 0 going here, I may be sending 5 here. See, a decoder was giving me 8 outputs, is it not? So instead of connecting to the 0th output, I might be connecting to another output. But at this level, the same row decoding will continue. Look at it over here, जो मैंने अभी पहले programmation chart दिखाया था. What is happening here? So if you look at the programmation, this is just 4 bits. Yeah. Look at this. For word line 0, 1, 2, 3, where would the programmation be? For the Are you able to see this? For the top 4 word lines, the programmation is always on the same A2 bar, A1, A3 bar. So instead of using 4 transistors there, I could have used just one. Because it is going to do the same thing. I may have a bigger transistor, but it still saves me area. Are you able to see this, everyone?
In this diagram, source and source is connected to the horizontal line, but
Sorry?
NAND gate are series. So source and drain of MOSFET should be connected to the horizontal line.
I'm not even showing that. I'm just showing the gate programmation. Yeah, because this is not a layout. This is just a cartoon to show you how the gates are programmed. This is not a layout. This is just to share with you how programmation is done. It's a cartoon. I have not shown neither the programmation of the source nor the drain. That's for you to work out. Something you will also do, na? Is it okay?
But this also, when we divide it into cells, this also is a constraint on the number of rows we can increase at a time.
Yes. So now you remember why I brought your attention to the step size when we were talking of a compiler datasheet. Go back to that compiler datasheet and see that the step size is not 1 when it comes to rows. It's always 2 or 4 or whatever the multiple is. It is always like that. It tells you what is the minimum step size that you will have in terms of rows. It has to be defined in the compiler datasheet.
In static decoding, the step is setup type involves the complete decoding integrates.
Sorry?
Setup time involves complete decoding logic integrates and static decoding when we use static circuits.
Okay. So when you use static circuits, where does the clock meet the address for the first time? When you use static circuits, where does the clock meet the address for the first time? Finally, in the post decoder. Are you with me? Finally, in the row decoder, where it has to select the word line, that is where the clock meets. So all the address decoding has to complete before the clock arrives. All that series of AND gates, NAND gates that we were just looking at have to complete their evaluations before clock arrives. Setup time increases. Now, what about dynamic? For the dynamic gates, even in the pre-decoding stage, you will have a clock interacting with the addresses, even in the pre-decoding. So how many gate stages do you have before the clock arrives? Just a few buffer stages and a latch. So setup time is less. Setup time is essentially a race condition. Do you realize this? Setup time is a race condition between my clock arriving at a particular gate or and compared with my address arriving at that gate. We discussed this in detail when we were talking about state machine and control logic. Did we not? We discussed that in detail in the class. Setup time is always about, it's like a relay race. The, uh, the system is ready and the clock comes, you should just simply be able to run. To be able to do that, the system should be ready. And that means that address should be stable at that particular transfer point. That is what your setup time is. The transfer point is far inside the memory. It means someone has to walk a much longer distance to be able to be ready and accept the baton. So you're giving me clues about what kind of questions I should ask you in the mid-sem exam. Good. यो आपको याद ही नहीं है हमने क्या बातें करी हैं क्लास में. Okay, any other questions? रोहित हंस रहा है. Is it okay? Should we move forward? So after that, we had started with mismatch. So with what is mismatch?
Variations on silicon that can cause the rise of amount of the same
Mhm. So in a layman's language, you wanted two things to be designed and operate exactly the same manner. They don't do it like that. So that is mismatch. And in any natural process, in any manufacturing process, this will happen. Uh, Natural process, for example, in this class, there is an expectation. Everyone will meet that expectation to a varying degree of levels. So that is mismatch. So this now when this happens with devices, it can lead to failure. When this happens in your circuits, inside your circuits, this can lead to a failure. And that is why it is important for us to understand mismatch in a little more detail. As memory designers, if you do not know what is causing mismatch, you will not know how to manage it. So I had specifically requested that before today's class, please watch the video on mismatch. How many of you have watched the video on mismatch? Thank you. So now it means that our class can be far more interactive today and we can go into the nuances of how do you handle such stuff. So there are two kinds of mismatch that we already introduced in the last session. They are random and systematic. What is random mismatch?
The intrinsic mismatch that is statistical in nature and cannot be detected.
So random mismatch is the mismatch which is intrinsic to a device fabrication process. It is intrinsic to the device. It is intrinsic to the process. You cannot control it. You can control it by instrumentation, you can control it by the machining and the process there, but you cannot say that, okay, this device will have more VT and this device will have lesser VT just by looking at them. Whereas systematic mismatches, if you know where the device is placed and if you understand the reason of that systematic mismatch, you can predict what kind of variation would happen in that particular device. So obviously, systematic mismatches are easier to handle than random mismatches. For systematic mismatches, what we typically do is we would try to model them in our simulations directly. In single simulation, you will be able to see the exact impact of mismatch. We talked about well proximity effect in the last class. We understand the physics behind it. We know that the impact on VT is directly proportional to the distance from my anvil. If you have the layout, can you ascertain that distance? You can. So now, since you can ascertain that distance, you also know the physics behind it, you can always model it in your simulations. In the device models in advanced technologies, you will see there is a variable called SC underscore A, SC underscore B, and so on. In 65 nanometer extractions, have you seen such variables? Have you noticed these variables in the extracted netlist? SC underscore A, SC underscore B, ST वाले extractions के अंदर? Just go back and look at it again. Okay. Otherwise, so what we are saying is that as you send the layout for processing, for extraction, you already know these distances. You can always put them in the model, in the extracted netlist. So that when the simulation happens, when you do the simulation, these variables, these values can be used to determine the change in VT. Similarly, you will also find another parameter called A. I'm talking specifically about ST extraction deck. In any other technology, you will the variable name, like it's something like X and P and Q and R. You could use, someone can use a variable X and another one can use a variable Y and someone can use a variable name Anuj. That doesn't make any difference. What you're talking about is the intent. That in ST technologies, you will notice that there is a variable with letter A. A is equal to something. That talks about the stress effect in terms of what is the extension of active region beyond the gate poly. So what we are now talking about is that if I know what is the physics behind a particular effect, for systematic variations, I can always model it. And then I'm not worried because I can see the impact of that systematic variation in my simulation directly. Single simulation, I will be able to observe it. Random variations, on the other hand, are, as the name also suggests, completely random. So one simulation will not help you. It is here that you need to run Monte Carlo. What does Monte Carlo do? Monte Carlo would say that, okay, you have this variable called VT. 10 types of reasons of variations in VT will lead to some distribution of VT on silicon. If I know the characteristics of that distribution, so if you have a Gaussian distribution, what all information do you need to characterize that Gaussian distribution? Mean and variance. So mu and sigma, these two are sufficient. If you have another distribution, you can again, there could be 3 variables at most. But whatever distribution is, that is the beauty of math now. All of you have done the course on probability and statistics. Now, उस समय पता नहीं आपको कितना समझ में आया था, how much of it did you value or cherish or understand, but now I am telling you is an application of what we learned there. Over there, we said that every distribution can be modeled by just 2 or 3 variables. It did not appear like a very big statement then, but I am telling you that all these variations that you have already watched in the video and we are going to review now also can be modeled just by 2 numbers. Just two numbers, and you can model all these types of variations without, even if you. So, how many of you ran Monte Carlo simulations in DVD also? Power, ye haath khada. You do not even know what kind of variations they are modeling. But you ran the simulation and you could see the impact of mismatch on your output. Are you with me? Now, if you had to do all the study to be able to arrive at that, how much longer you would have taken? Now, just because of math and someone telling that there is a formula for Gaussian distribution and just mu and sigma, you know, and you can now anticipate, predict what kind of variations will happen on silicon. Are you able to see this? So for random variations, you have nothing else to do but to run Monte Carlo simulations or do Monte Carlo analysis and arrive at estimate of variations on silicon. Now, in advanced technologies and with advanced tooling, uh, we have more advanced methods of estimating impact of variations. We'll look at those also. But Monte Carlo is the most basic one, or the first one that was brought in, and others have made improvements on Monte Carlo. So we will stay with Monte Carlo in the class, in the project, but be aware, and we will talk about other tools like Solido, which is design of experiments, or importance sampling. We will talk about those also towards the end of the session today. Okay. Or when we will talk about verification. So, as I said, systematic variations, if you have the information of the layout, you can always model them. Uh, you can either improve the process, you can either model them, or you can then relax the design rules so that those systematic variations do not bother you.
Sir, it's kind of just called pseudo random variation. So what does it mean? Even what does it mean by something being event? Like what kind of?
So, what kind of events are we talking about? You remember when we were talking about clock jitter? कहाँ पे है pseudo random? Okay. So when we were talking about clock jitter, we said that, uh, or clock variations, we said that due to IR drop or due to something, there will be a drop that will happen here. And therefore, the clock can arrive a little early or arrive a little late. Now, is this a random variation? So you know the physics of it entirely. And if you know the stimuli that is going to activate my particular network, you can also estimate the kind of things that would happen. They are systematic variations, but still random. अगर आपका stimuli वैसा नहीं आया तो उस तरह का क्रॉस टॉक नहीं होगा या उस तरह का एयर ड्रॉप नहीं होगा, and that variation may not come. So that is what is being referred to as pseudo, which is depending on your event they happen, they cannot be really modeled, and therefore you have to still handle them as random variations. They are systematic. You know the physics of it. You know the why this variation is happening. All of that you understand well, and you can even predict कि अच्छा clock अगर इस समय आया तो ये होगा. But you cannot predict really if the clock will come on in the field at that time. So you have to still use it as a random.
So
You have to margin it as a random variation.
So if we consider something like coupling or something like that, would that also, I mean, in terms of that would also be kind of event dependent. Like if you have that event, only then the coupling will because it might not.
Yeah, we looked at the impact of Miller capacitance, Miller coupling. So yes, that you can model based on events. But suppose in STA, do you know which event will happen? So you have to margin for it. In a dynamic simulation, you can see the impact. So that is where it is systematic. But when you're doing STA, you still have to plan for the worst case. Are you with me? So as we said, systematic variations, you can model them, you can avoid them, or you can change the DRCs so that those variations are limited. Uh, this was, for example, how the poly width, which is the length of your device, changes when we are talking about putting it actually on silicon. You made very cute rectangles. See what happens to those rectangles over here. We already saw part of it or evidence of it even when you're talking about regular high density memory cell. That with the beta ratio of 1 itself, the cell ratio of 1 itself, I had finally better yield than with a cell ratio of 1.4 or something like that. So denser cell, better Wieman. So that is what happens. Because on silicon, whatever you had drawn will not come out as those clear rectangles. What that means is that the speed of your devices, the VT of your devices will be different from what you had anticipated in your simulation. But given your technology, given your uh, layout rules, this can be predicted. And therefore, it is called as a systematic variation. So we looked at so many DRC violations that we do in memory cells. There are tools to model all these variations on layouts, and whatever violations you are doing on the memory cell, they are run through Monte Carlo simulations on those tools to see what is the impact of those rule violations on overall yield. If the impact is significant, the only for the memory array, the optical proximity corrections, the resolution enhancement techniques are tweaked additionally so that we get the desired yield, we get the desired output there. But because it's a systematic variation, you can run a Monte Carlo simulation and do something about it. Are you able to see this? Layout तो आप भेज चुके हैं ना? The only option is to change the mask now. Layout to you draw, you made, and then you sent it for fabrication. Now the resolution enhancement technique will work on your layout, make it process friendly, and then make the masks. Okay. Then we also had proximity effects. Yes. Edge bias. So it is about when you have multiple lines running, the end line will have, because it's on the edge of the structure, will have a different bias, a different kind of, let us say, bending or shrinking or whatever than the remaining. So to avoid this, again, this is a structural thing. To avoid this, DRC is changed. What I said is that when there is a array of or a series of polys there, you add one more poly in the end. We call it as dummy poly. That poly you will not use as a transistor. It is sacrificed. We know it will not be formed correctly. So you will have lots of such dummy poly and sacrificial polys and sacrificial structures, metals in your layouts in advanced technologies. And this is put as a DRC because this is a systematic variation that you can always model.
But then you have said in the later lectures that we don't put dummy polys in memory because of predictability. So
In the memory cell, we do not need to put dummy polys inside the memory cell. But in the periphery layout, there may be a need to put dummy polys because no one can optimize the memory periphery layout for or RET techniques for memory periphery. People can be designing them in any different way. They are like logic.
how do we model this in the memory cells? We give margins or
No, we just simulate it on the. So we make a huge array and we just simulate it. We just simulate the entire thing, and we see that what is the impact on fidelity of the structures that I wanted to create. And if the fidelity is as I desired, I don't do anything. In memories, we do not make dummy polys. In fact, what we do is we actually surround the memory array, entire memory array, with a pair of, or with a pair name, with a set of, uh, what do we call them, shadow rows or something like that we put, uh, which are not accessed. So they are not replica rows. They are just there to give the environment to the memory cells. So this is, see, we were talking about banked architectures. है ना? हमने कहा था कि there will be banks that will split our memory into. Now सुनने में लगता है ठीक है. You know, you just break the bit line here, break the bit line here, break the bit line here, and you will have multiple bit lines available. But in reality, whenever you break the bit line or whenever you have to give a little break in the memory array, you actually have to give a buffer of a few rows which are sacrificed, which are not used for any other thing. Because you know that there will be variations that are unwarranted, that are unplanned for, or that are not modeled in our models. And therefore, if I start to use the cells in this buffer region, those cells will fail. These are called environment cells. Rows and columns both. Word line end cells, bit line end cells, all of them. We have to put them so that we are able to ensure that whatever rule violations we have done inside the memory array, they do not impact memory functionality. Otherwise, those edge memory cells will behave very differently from those in the center. So you do not let the edge cells to be used at all. You add environment cells, you add end cells at the boundary of the entire array. And if you've broken them into multiple banks, then at the boundary of every bank. Is that okay? So proximity effects. When the STI between two different devices is very small, the stress linked to that STI can propagate until the gate of the device and result in different current and different VT. This was not a problem until we used low cost, that is the local oxide layer something. But STI has been in place for many, I would say, decades now. And in the presence of STI, we already start to see stress effects. So those stress effects are systematic. We know that the stress will propagate in a particular manner. We can model it, and therefore we design it appropriately. Now, what does it mean for memories? See, do you remember the layout of the memory cell that we were looking at? In the memory cell layout, we have a continuous active which goes something like this. Here is a pass gate, pull downs, Do you see this? There's a continuous active. Only at the end of my array do I see something like a contact and STI. At the fag end of the array, I see that. Everything is otherwise continuous. As designers, if you want to emulate the same behavior in any other circuit, you have to have the same contiguous active region so that the stress effects are similar. Are you able to see this? So for example, if you want to have a replica bit line, it should have the same structure in terms of active as actual bit line. If you want to make a replica word line, the cells and those cells are expected to discharge, then that should have the same structure as the actual word line. If you want to make a row decoder, a dummy row decoder or a replica row decoder, it should have the same proximity effects as the actual row decoder. Because you want to match actual row decoder in your design. Similarly, about write driver, we looked at the constant negative voltage write driver paper that day. Now, that was just the schematic that they showed you. But when you make the layout, on the replica side, the replica write driver has to have the similar proximity effects, similar structural variations as actual write driver. See, one may say that, why do I need to know all these reasons, sources of variations? They can anyways be modeled. You need to know about these sources of variations so that you can do better matching. And matching is of a lot of essence when it comes to memory design. Are you able to see this? And you notice the proximity effects have a significant impact on variations, on delays. So this impact cannot be ignored easily. So you better do the matching well. We have had, so we'll probably talk about it later. You might have already seen that session. Uh, where I was talking about a failure that we observed in a particular memory because word line was running in metal 3 and the precharge was modeled or was drawn in metal 2. So metal 3 and metal 2 are two different process steps altogether. Metal 2 may be made thicker or thinner, and metal 3 could be on the other side of the uh, acceptable specification criteria. And the resistances of the two lines could be very, very different. So whichever signals you want to match, they should be drawn in the same metal. So there are so many things that you have to take care of when you are doing matching. We talked about common centroid layout already. So you will see that matching has been a consistent theme, just like area is diamond has been a consistent theme, sharing has been a consistent theme. In this program, we've also been already talking about matching in one way or another to you across various sessions, various lectures. So this is a pervasive theme there. And this session is about really giving a theoretical basis of it. Why you need to do that? Because these variations are observed on silicon. Are you able to see this? Then yes, there are pattern-dependent variations. We talked about dishing in DVD also. What is dishing?
Because copper was
So chemomechanical planarization is a process in which the surface of the wafer is planarized. Now you have chemicals and you have physical scrubbers actually moving and scrubbing the surface of the wafer, cleaning the wafer in a way. Copper is much softer than oxide. As a result, when the same pressure is applied on copper and the scrubber runs over them, they take away more copper if there is a lot of, if there's a big pool of copper there. That is what is called as dishing. You see? At other places, there could be erosion, but at places, there can be dishing. Now, all these, what does this do? This changes the resistance. This increases the resistance of those wires and it reduces their capacitance. At least sidewall capacitance reduces. If you are designing something to model another wire, you have to ensure that even the density of wires is similar across the two regions. So a replica bit line could be thousands of microns away from the real bit line that you want to track, but you still have to maintain the same metal 2 density when you are modeling the bit line. This also emphasizes the fact that you cannot have tracked signals in different metal layers. Obviously, because different, in one layer you had a little bit more CMP, in another layer you had a little bit lesser CMP, and the wire resistance and capacitance behavior will immediately change. Matching is no longer there. Are you able to see this? Yes, that is why I said the same density of metal has to be ensured wherever you want to do the matching. Otherwise, dishing will be different. It is expected, it is going to be different, but whenever you are doing the matching, ensure that the metal density remains same. It cannot be that you want to match a wire of zero 0.1 micron thickness with another wire of 1 micron thickness. Oh, capacitance to same hai na? No, it doesn't work. If you want to make so how many of you notice that when we were talking about this negative bit line, constant negative bit line right driver, I had mentioned, and it was also written in the paper, that the capacitance of the replica bit line is 2 CBL. How many of you noticed that? Oh, just few of you. So now I want to have a multiplicand of CBL, not exactly CBL. I have to double the capacitance of CBL. What would I do? I will actually use 2 bit lines. I will not say, oh, 2 CBL lane ke liye, I will increase the width. Or I will put one more metal on the top of this and then short them. That is not how you will get 2 CBL. In different process conditions, it might be 2 CBL, it might be 2.2 CBL, it might be 1.8 CBL. The variations will be very, very large. So you model it, that 2 CBL, by actually using 2 different bit cells next to each other and connecting their bit lines. Are you getting it? So you could have increased the width and said, हाँ देखो इसका plate capacitance double हो गया. That's not the right way to match it. So आप लोग डिटेल में देखते नहीं हो. Only 5 people notice that we're talking about 2 CVL and you're talking about the replica bit line there. Details are important. And we also in DVD itself talked about the fact that you can use dummy fills or slots to avoid unnecessary extra dishing. Even when you're not matching, you do not want dishing to happen because all your delays you have, all the STA that you've done with the assumption that this is your wire resistance, this is your wire capacitance. If dishing just keeps on happening everywhere, then that's not a good thing. All your timing estimates will go for a toss. So whether you are matching or not matching, you still, as a design artifact, have to ensure dummies are put or slotting is done when you have very wide wires. No. 2 CBL was used because of some other reason. I'm just saying how to implement that 2 CBL is by using 2 columns instead of by just making the bit line wider.
These replicas are made exactly the same way what original circuit is.
So she's asking the replica is made exactly the same way. See, if I had allowed to increase the metal width, then I would not have added one more extra column and I would have saved area. Yes. But it's being penny wise, pound foolish. The variations that it would introduce can result in yield loss. So whatever you saved, whatever minimally you saved in area, you lost in terms of yield. So as memory designers, if matching is required, no compromises. Yes, you can think of ways to geometrically arrange your stuff in such a way that you can still save area. So area remains to be diamond, but if you have no other alternative and area has to go, then area has to go. But matching has to be ensured because functionality is above area. If something is not functional, what will you do of area? Are you with me? So matching leads to loss of if you do not match well, it can lead to loss of functionality. Forget about the diamond, you will not get it at all. Is that okay? And now we come to what is random mismatches because of random dopant fluctuations. So what are random dopant fluctuations?
That we desire to get some particular number of dopants, but they can increase or decrease. There could be variation.
Okay, the number of dopants could be more or less in a particular channel region. What else is random dopant fluctuations? The dopants might be placed at different locations in comparison to my source and drain region. So the potential field across the entire channel region will not be same. What else is random dopant fluctuations? हाँ, वो जो इलेक्ट्रिक फील्ड ही चेंज कर दिया तो मोबिलिटी तो चेंज हो ही जाएगी. Yes. What else?
Can they be stuck in the lattice of the state? Like when we do some relative plan of this, so
That is anyways done, na? So that is a process of ion implantation. So what is ion implantation? We studied that in the first part of how many of you doing IC fabrication course? Oh, just so few of you. So in IC fabrication, we talk about all these aspects. That ion implantation, we also talked about it in DVD, by the way, that you throw ions from the top, they will settle somewhere, then you heat it, do some thermal annealing, they will diffuse. But that diffuse is a natural process. Something will diffuse 10 microns, another thing will diffuse just 1 micron. We don't know.
that also dopant.
That is dopant fluctuations. That is what is changing the place where your dopant is placed, how close to the channel it is. That's stronger than influence that dopant atom would have on the channel. So it is not just the depth, it is not just the proximity from either source or drain. It is not just the number of dopants, but all of them together and many more things which come as a part of random dopant fluctuations. Okay. Now, can you preempt? No. So this is truly random. And therefore, you can only model it through Monte Carlo. Now, in advanced technologies like fully depleted SOI or FinFETs, the substrate is depleted. Depleted means there are no dopants. So this biggest cause of variations in earlier technologies, so 28 nanometer tak, this was the biggest cause of variations. But when 28 nanometer FDSOI came, or when people started to use FinFET subsequently, this biggest cause of variations was taken away. So in 28 nanometer, if you look at it, you will realize that same technology, 28 nanometer in terms of same machining is being used, but an FDSOI design can go to about 100 millivolts lower than a bulk design. So when I started my PhD, uh, at that time, I was targeting 28 nanometer bulk. And I said, okay, we will go to 0.45 volts because 0.45 is a very, very low voltage for bulk. But 1 year into the PhD, FDSOI technology came. And all of a sudden, the variations were not there. 0.45 could be achieved just like this. Not just like this, but yeah, it was no longer that big goal that we would set for a PhD program. So we sat together and we said, no, 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 no. Now 0.45 is not as interesting. If we really want to make some meaningful contribution, we will want to go to 0.35. See, I was not working on the technology side of things. I was working on the design side of things. And when the technology gave us some benefits, my PhD would become redundant if I was going to use those benefits to demonstrate the gains. So we set the target 100 millivolts lower. We said 0.35. Are you getting it? So this was the biggest source of variations. Random dopant fluctuations was the biggest source of variations until we went to fully depleted substrates. But that doesn't mean variations reduced. Variations in the same technology remained significantly reduced. But in FinFETs, for example, now there are new kind of variations. Fin height, fin tapering. All those things are new kind of variations which were not there earlier. And they clearly have an impact on how my device would behave, what kind of current it would have, what is the VT there. So what we did observe, and you are already working on 65 and random dopant fluctuations are a big thing there. What we observed was that if in a particular axis I was to make VT slow, VT tip, and let us say VT fast, and now show variations at given lot. When my lot is still designed as typical or fabricated as typical, there would be few devices which would be as slow as the slow lot, and a few which will be as fast as the fast lot. And the same would happen over here. And notice that when we said that 3 sigma variations would happen on my VT, we have kept the sigma variation to be 30 millivolts, something like that we had put. 3 sigma plus minus 90, and so this could be 80, and 3 sigma variation from this could be taking a device here, even faster than typical. So local mismatches or random variations were a significant uh, challenge because of random dopant fluctuations. As soon as the random dopant fluctuations were taken away, this improved. But then in advanced technologies, other sources of variations get added. So they kind of more than have, they've eaten away all the margins or all the benefits that random dopant fluctuation avoidance had taken away. Is it okay? Any questions?
Advanced technologies, this variation kind of just increases.
Not advanced technologies. In 28 FDSOI, so this was 28, the earlier curve. In 28 FDSOI, because random dopant fluctuation was not there, the variations reduced. That was why we were able to see a significant reduction in VDD min.
This plot, like this is only considering random dopant fluctuations.
This is considering every variation. If it was only random, then I would have said this only, no? I would have shown an impulse over here. Everything is here. No, there are many other variations. We're talking about them now. But because random dopant fluctuations vanished from 28 bulk to 28 FDSOI, we saw a significant improvement in variability. So, interface roughness. What is interface roughness?
Like when we grow the silicon dioxide on the side also. So the molecular placement varies.
See, the gate oxide thickness that you use in, let us say, 65 nanometers or 28 nanometers is of the order of 10 to 18 angstroms. Matlab 1 to 1.8 nanometers. We're talking of a very, very small scale. And whatever VT nominal you have been told is for a particular gate thickness. TOX. See, TOX has a very strong role in the determining the capacitance of your device. Na? Now, how many molecules would come in that thickness of 1.8 nanometers or 1 nanometers? What is the size of one silicon molecule? What is the size of an oxygen molecule? How many molecules of silicon atom and oxygen atom, and how many molecules of silicon dioxide are we talking about? In that 1 nanometer or 10 angstroms or 18 angstrom thickness. We're just talking about 2 to 3 molecules. Now, let us say there were 2 molecules stacked right one over the other. There would be one thickness. There is another part in the same gate where these 2 atoms are next, a little next to each other, displaced vertically. Some other thickness. Another place, just sitting next to each other almost. Another thickness. So what we are talking about is that, and then poly is above it. What we are saying is that the gate oxide thickness is not a constant 12 angstroms that I told you. It is 11 angstroms somewhere, it is 10 angstroms at another place, it is 15 angstroms at another place. Averagely, it is 12. Are you getting it? So what we are saying is that interface is not very smooth. Interface, as you see, kahin pe 2.2 nanometers, kahin pe 2.4 nanometers, 2.6 nanometers in this example. Interface is rough. Average we have given you. But in reality, if something like a thick gate oxide happens closer to source versus it happens closer to drain, the response of my gate could be different. Are you able to see this? Just like random dopant fluctuations, where my dopant is, it would change the electric fields exactly the same way. If it is a little thicker there is lesser gate control. If it is a little thinner there is more gate voltage control. So all that is going to impact your device behavior. Can it be predicted? No. Same device, same layout, everything is same. The behavior can be different because you cannot predict which place your thicker gate would be and which place your thinner gate would be. When you're talking about just 0.01, 0.02, or zero point 0.1 movement of gate oxide there. Huh? So this roughness causes variations. Similarly, line edge roughness. You watch the video. Line edge roughness is discussed in a lot of detail in the video itself. Any questions about it? So what we observed in one of our silicons was that when we were using very small lengths, uh, our devices were becoming slower than what we wanted them to be. See, when you're using small lengths, you expect the device to be faster actually. But in our experiment, what we noticed was that, oh, the gate is not really responding the way it should. The device is not really behaving the way it should. And what we then realized was that the polycrystallines, the crystals of the poly, are big. So line edge roughness was very, very large. In fact, the flow of current across the entire gate was severely hampered. And therefore, ST then changed the process in which it would deposit polysilicon on wafers so that the crystal size is smaller. But line edge roughness is is a significant contributor of variation in advanced technologies because your gate length or channel length is very short. Because that channel length is very short, even a very small variation has a significant impact on your conductivity. Is it okay? Any questions about line edge roughness? We've actually discussed this in a lot of detail in the video also. You understand line edge roughness? All of you? Hmm?
The line edge roughness only depends on the anisotropic behavior. So if we take example of suppose single crystal silicon or gallium arsenide, then line edge roughness won't have any impact.
Okay, let's look at it. We are talking about poly. When we are fabricating the gate, we're using poly gate there. And that poly is polycrystalline. Poly, the name is polycrystalline. So line edge roughness is always going to be there. We are not talking about the substrate at all. We are talking about depositing a layer of poly and then etching it out. You cannot deposit one single crystal of poly.
Yes.
Poly means polycrystalline. So line edge roughness, I'm not able to relate where this question is coming from.
So we it's discussed in lectures that line edge roughness is based on the anisotropic behavior. So we etch differently in the different directions. So
Yes.
this anisotropic behavior is not about the substrate.
Substrate is fully crystalline. So we're not even line edge roughness. We talked only about the gate length varying at different places because the crystals could be placed differently. Crystal size could be different. They could be placed differently. Is it okay? Clear? So what did we do? We said this is the poly that I want. अलग अलग तरह से आपका crystalline structure होगा. So somewhere there would be a very thin poly, and at other places there will be a much thicker poly because of the polycrystalline structure itself. And that is what is line edge roughness. This is not about the substrate there. This is about the gate being fabricated with multiple crystals of poly coming together. Is it okay? So this is also a random variation which you have to handle there. Okay. And this slide actually just quantifies the impact of same kind of variation across technologies. See, line edge roughness ऐसा नहीं है कि अभी अभी नई टेक्नोलॉजी में आ गई. Line edge roughness was always there. Let us say line edge roughness always caused 5 nanometer of variation. So what are we talking about? We're talking about a situation where as we move to an advanced technology, the impact of line edge roughness has gotten amplified. Are you able to see this? Even the interface roughness was always there. Let us say it was one angstroms. The impact of that has got amplified in advanced technologies. Are you able to see this? That is why आप कुछ और करो चाहे ना करो, एडवांस टेक्नोलॉजी में मिसमैच तो और बढ़ेगा ही बढ़ेगा. And that is why, as we move from one technology to another, the role of a designer becomes all the more important. Because technology will only hamper you, stop you from extracting better performance. It will only necessitate leaving more margins. And that is where we as designers have to think of innovative solutions to still improve performance, still reduce power, reduce margins somehow. That has to be done through various ingenious ways in circuit design, in layout design, and overall architecture design. Are you with me? So, just by the virtue of going to advanced technologies, we are going to see a bigger impact of variations on our circuits, just by the virtue of advanced technologies. And you have to learn how to handle those. So, this then is a list of various steps and how different actions, for example, an implant, what could change? Implant energy could change, dosage could change, tilt could change, gate length profile affects halo implant position. You see, इतने सारे steps हैं आपके silicon fabrication process में. Every step, just a little bit of an angle change of the machine, of the where your die is on the wafer. If it is on this corner of the wafer or this corner of the wafer, that could change. So there are so many sources of variations in the entire process. Little by little, they accumulate and they make it difficult for designers, like SRAM designers specifically, to design. Is it okay? And in addition to this, we also have these environmental variations, IR drops happening, crosstalks happening, uh, jitter coming into picture. All those things are also there, which we as memory designers have to accommodate, design for, and add into our verification design flow. Is it okay? So, जितना भी हमने even DVD के समय, we said, okay, this is VDD nominal, this is VDD min, this is VDD max. All those are environment variables which are changing and they can change. Why would VDD supply change for a particular chip? Why would the VDD supply change?
That circuit you have made to somehow supply the VDD guide itself will also have some variations.
So the voltage regulators would have their output variations, load. We've done amplifiers, class A, class B amplifiers. So you talked about load regulation there. उस समय समझ में नहीं आ रहा था ना क्यों करवा रहे हैं. If you don't make a good amplifier, if you don't make a good regulator there, you'll have more environmental variations here. Then your battery may not be fully charged. The power side, the power regulation that we're talking about when we design amplifiers again, those could change. So many reasons why VDD can go up or down. You target it to be 1.8, it may go to 1.92, 1.98. We usually say plus minus 10%. And in addition to that, there could be IR drops. In addition to that, there could be couplings that could come in. In addition to that, there could be temperature variations that could come in. You will be operating at room temperature, or if your chip is put inside a bonnet of a car with an internal combustion engine, the temperatures could simply be at 125 degrees Celsius, 175 degrees Celsius. If it is on the rooftop, let us say in Canada, the temperatures could be minus 20 degrees Celsius. So your chip could operate in multiple environmental settings. And as a designer, you have to ensure that variations across all such environmental conditions are also accounted for and margined well. See, memories are very, very sensitive to variation. See, you talk to analog designers, they will say, oh, we are very sensitive to variation. So what we've done is we've done a compensation block. So with the compensation block, you will see that our output is always within plus minus 1%, jitter, plus minus 1%. Now we tell them, okay, now do that with the sizes that you have in the memory cell. No, 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 that is your problem. You do that. They don't know how to handle this. However high and haughty they might appear to be, and हमने तो variation को tackle कर लिया. The fact that in memories you cannot really go to large lengths, you cannot really go to large devices to handle variations. Uh, it's a big challenge that we as designers have to face in memory design. Okay? So this is about modeling, as I already said. You've heard about SSTA now, statistical STA. Now, though, all of you have heard. When Professor Gupta was conducting his guest lecture last semester, there was some confusion about what is SSTA, but now all of you know SSTA. Am I right? Statistical STA. So, see, initially, when this tutorial was given in 2006 or whatever time frame, at that time, uh, people were just modeling either rise or fall delay for a NAND gate or a NOR gate and saying that, okay, one delay is sufficient for characterizing the entire gate. But then at this time when this tutorial was being given, already in the industry, there was some implementation of different rise delay, different fall delay. In memories, we had already started to implement that. There is a different access time for bits which are closest to the control region and bits which are farther away from the control region. Why? Because my word line has to travel this much more, my sense amplifier trigger has to travel this much more. So my output will come a little later for the farthest bit and will come a little earlier for the first bit. Setup time will be different for this bit versus that bit because my clock is getting very delayed when it goes to the last IO. So my data can come much later. The clock is coming so late, the data can also come late. But for the first IO, it has to come early. So setup time and hold times were characterized now bitwise. So why? Because now the standard hand waving approaches of okay, चलो इसके लिए 1% margin छोड़ दो, इसके लिए 2% margin छोड़ दो, were no longer working. We realize that we need to be accurate. We need to be accurate to be able to extract the performance from silicon there. So even in verifications, we will talk about them in the next class. Even in verifications, what we saw was that these OCVs, जो आप ऑन चिप वेरिएशंस के लिए जो आप मार्जिन्स छोड़ते हो अपने टाइमिंग एनालिसिस में, they were becoming exorbitant. Memory performance is not improving. Memories are in the critical path everywhere. And customer is expecting that you will be able to operate the system at a double the frequency or at 20% higher frequency. How will you get it? So people started to look at every place where they were leaving margins. And they said, oh, I don't want to give OCVs. So what do? I don't want to give OCVs for variations. You characterize the memory with statistical timings. So this need started to come at that time. And today SSTA is what is typically done. We don't want to leave margins for hold and access time both. You characterize per bit so that we are more accurate. So there is a much stronger focus on accuracy at the characterization level so that at chip level you can reduce the OCVs and somehow gain performance. As designers, we were struggling in a different way. What we noticed was that distributions which we assumed to be Gaussian were no longer Gaussian. Because if you take the Gaussian assumption, current will become negative. The currents were reducing as we moved down the technology node. Device size has reduced, everything is scaled. So currents were also reducing and variations were increasing. So there was a time when we said nominal current minus 3 sigma. Let us design with that. But now in advanced technologies, nominal current minus, because the capacity has increased, we want to qualify higher sigma extent. Nominal current minus 4.5 sigma was negative. Now, how do you design with a negative current? So we actually designed a completely new verification methodology where we said, no, this current is no longer Gaussian. Since it is not Gaussian, we had to use different distributions. We use Weibull distribution to model minimum current in any bit slice. So we talk about that in one of the next lectures. But when you will enter into the industry, you will realize there is a much stronger focus on accuracy today than it was even when these slides were made. Okay. So uh, be prepared for that. And if you miss out details like replica write bit line had 2 CBL, your system will fail. You have to really be very, very meticulous and look into the details when it comes to memory design. Is it okay? So next class, we'll look at how we use statistics in much more detail and what kind of verifications we do. Verifications is something which is very, very important in context of memory design. And we'll spend some time on that. We'll talk about Monte Carlo. We'll talk about design of experiments. So it is going to be an interesting session and will prepare you well. Okay. It's good if you can come prepared. It will make it easier for you to understand all these concepts which are nowhere there in the books. And you will have to otherwise read thick papers to understand what important sampling is and things like that. Okay. All the best.